Welcome everybody to Algebra 2. We've got our 4b chapter, and this is section 3b, 4b, 3b. We're solving polynomial equations, and we saw in the first part of 4b.3 that way back when, in the days of yore, that was quite an exhaustive process. We had big-time math thinkers like Descartes coming up with ways of solving polynomials and figuring out what could be potential rational zeros. And then Descartes' rule of signs, what are our possibilities as far as positive versus negative real zeros. Really just a lot of work on their part. Then we would test with synthetic division over and over to see what would divide cleanly and produce a factor. It was quite an exhaustive process. So now what we're going to do is we're going to compare that work with how technology can help take some of that guess and check, trial and error work out of solving higher degree polynomials. So we'll be using a TI-84, but please realize that you could use other tools. GeoGebra or Desmos can also get this work done as well. We just need to be able to make a table of values. Heck, Microsoft Excel could even do that, or Google Sheets or something. So anyway, let's see what's going on here. So our steps. You'll notice instead of looking at possibilities, now we're just going to go straight to the calculator. We're going to type the function into the y equals menu, and then it's tempting to want to look at the graph, but the graph doesn't really help us a whole lot because polynomials grow incredibly quickly, and you will see that when we look at the table in a little bit in our first example. But we're going to go through the table instead and find an x value that produces a matching y value that is 0. This is the same thing as trying synthetic division over and over again with different x values. We're looking for that 0 output. That means we had a factor. That means we had a solution. Then we're going to use synthetic division with that x value that we gathered from the table to kind of divide down our polynomial until it's something manageable. So step 4, we're going to repeat that process if we can until we end up with something that is a factorable polynomial, or it's something that's a quadratic, so we could use things like quadratic formula. Once we've reached that point, we're going to refine the remaining zeros by either doing more factoring, actually using the quadratic formula, or by taking square roots. Pretty short lesson today. Here's our first example. Now, example 1, as I look at this, I see the 1 and the 7, the 9 and the 63, and I'm thinking, hey, this might be something that I could do just by doing factor by grouping, and it looks like I quite possibly could. However, to introduce the steps for this one, let's bring up our calculator. We're going to assume that we don't see any factor by grouping whatsoever. So in the calculator here, I'm going to try and go nice and slow to hopefully allow you to follow the mouse cursor here. In the y equals menu, that's this button in the top left, you guys are probably familiar with this. We're going to type in x, here's the variable key, to the, that's the caret key underneath the clear over here on the far right. Third, if you have a newer calculator, you may have to hit the right arrow key to bump you down out of the exponent. And then we'll just continue. Let's see, minus 7x squared plus 9x minus 63. And again, it's tempting to hit the graph, but if I hit the graph, you'll see it doesn't really help us a whole heck of a lot. So we want to hit instead second graph to look at the table. And we're just looking at these x values, which one has a matching y value of 0. So we're going to have to use the arrow keys to look around, and you can see if I go to the left, look at how massive negative those numbers get. So we're not really getting closer to where we want. Right there. When x equals 7, y equals 0. So I'm going to hang on to that and go back to my work here. So we found 1 0 in the calculator, and just for my knowledge as your teacher, what you're going to put is via calc table, x equals 7 is a 0. And that tells me a whole lot. It not only tells me that you use the calculator to start the problem off, but it also shows me that you use the table feature in a calculator. So a very quick way of giving me, as the teacher, a lot of insight on how you found that 0, that starting point. All right, so from there, we take our x value of 7, and since that's a solution, we don't need to change the sign or anything. It goes right into the box for synthetic division. We'll use synthetic because it was a nice, quick way of dividing down a polynomial. And since the calculator told me the output was 0, that should be indicating that the remainder is 0. I'm sure hoping to see that as I go through my steps in synthetic. So it's kind of neat that this is actually checking our work as we go along. So we'll drop down the 1, then to the box 7 times 1 is 7. We'll add down the column, negative 7 plus 7 is 0. Back to the box. So sorry, these aren't decimal points. This is just me kind of trying to help you see where I'm looking. Let's see, so we got back to the box 7 times that 0 produces a 0. We'll add down the column, 9 plus 0 is 9. Back to the box a third time, 7 times 9 is 63. And sure enough, when I add down that column, that makes a total of 0. So we've confirmed not only that we found the correct value out of our calculator, but also that we typed it into the calculator the right way. If we had made a mistake typing into the calculator, this synthetic division would likely show us that because we wouldn't get a remainder of 0. All right, so what we have to do from there is find the remaining zeros. I know that this is a third degree polynomial, so it has 3 zeros, either real or imaginary. We've found one of them. There are 2 others. The result of our synthetic division, this 109, represents 1x squared plus 0x plus 9. So I'm going to take that, now that we've divided out the solution of 7, I can find the remaining solutions through this depressed polynomial. And for this one, since I'm just solving for x, let's go ahead and subtract 9 from both sides. And then all we have to get rid of is the second power. So here I'm able to square root both sides, and I get x equals plus or minus the square root of negative 9. And square rooting a negative, we learned that back in section 3.2, this just indicates that we've got imaginary solutions. So we called it a bluegill here, plus or minus I times root 9. That takes care of the negative underneath that square root. And then the square root of 9 is just 3. We were fortunate to get a perfect square number there, so I've got plus or minus I times 3, or just 3I. So to finally answer the question, our zeros, we had the 7 that we got from the calculator, we got a positive 3i from our square root work, and we also got a negative 3i from the square root work. Remember, these imaginary or irrational solutions that we get when we square root both sides or use quadratic formula or something, they always come in conjugate pairs. So that's what we see here, positive 3i and negative 3i. 1, 2, 3 zeros for a third degree polynomial. It fits the fundamental theorem of algebra. Right? But that's pretty slick, right? If you look at the work that's on the screen right now and you think back to all the times we had to go through synthetic, the list of possible rational zeros, this is saving us a tremendous amount of work that we would have to do by hand. So very grateful for that technology, to say the least. All right, our second example. Here we've got another cubic, a third degree polynomial, so I'm expecting 3 zeros coming out of this one. I'm going to bring the calculator back up, and we'll go back to the y equals menu, clear out what was there. We need to find a 0 to begin with. So let's see, we've got 2x to the third plus 13x to the second plus 8x minus 48. All right, I don't want to look at the graph, I just want to look at the table. So second graph will bring up that table. And, there, at x equals negative 4. So don't be surprised if you have to use the arrow keys to move up and down to find that first x value. In this case, we had to move a little bit, but ultimately we found it. So x equals negative 4. I'm going to hang on to that one. So let's see, again, it was a third degree, so we're expecting 3 zeros. That's what the fundamental theorem tells us. And then through our calc table, we found that x equals negative 4 is a 0. So let's use that 0 to divide this down with synthetic division. And again, I sure hope I get a 0 remainder. If I don't, I may have to go back to the calculator and check over some things. We'll drop down the 2. Negative 4 times 2 is negative 8. Add down the column, 13 and negative 8 is 5. Back to the box, negative 4 times 5 is negative 20. 8 plus negative 20 is negative 12. Back to the box. Negative 4 times negative 12 is a positive 48. Hey, and those add up to 0. All right, we're feeling good. All right. So, again, we already know that we have x equaling negative 4, but then when we get to this point, the polynomial we're left with is 2x squared plus 5x minus 12. That's what those 2, 5, and negative 12, that's what those numbers represent, that polynomial. And that's where our remaining zeros are going to come from. And we have a couple different options here. It's a quadratic, which is good because we can either try to factor that quadratic with magic numbers, or we can try to maybe use quadratic formula. So if you were sitting in my class, you probably heard me say to factor is faster, so try to factor first. Quadratic formula takes so long to simplify your answers. If we can factor this thing, it's going to save us some time. It does have a leading coefficient that's not 1, though. So we have to do 2 times negative 12 to get negative 24. What magic numbers will multiply to be negative 24 and add up to a positive 5? Well, that's 8 and negative 3. And if you think back to the start of chapter 3, remember we're trying to find zeros. Where does that blue polynomial equal 0? We picked the easier magic number. In this case it was negative 3. And I want to take a piece of the 2, a piece of that negative 12 to make my outside product be negative 3. In this case that would be 1x and negative 3. First times first, had to make 2x squared. That means this has to be a 2x factor. Last times last had to make negative 12. That means this has to be plus 4. And again, if you've practiced this through chapter 3 and in previous courses, you probably have this factored out before you ever even finished writing the minus 4ac in your quadratic formula. So what do we get out of these factors? Well, x plus 4 produces a negative 4 for a 0. And now that's important because we said negative 4 was a 0. Remember, we talked about how multiplicity, husband, wife, brother-in-law, comes into play here. It's possible to get the same 0 multiple times. So we didn't do anything wrong here. We didn't mess up any negative signs or anything like that. It's just that solution showed up twice. And then the other factor, if I were to solve that equal to 0 by itself, I would add the 3 and divide by 2, positive 3 over 2. All right, so the zeros of this polynomial are x equals negative 4. That had a multiplicity 2. It counts twice. And we had a 3 over 2. So that's 1, 2, 3 solutions for that third degree polynomial. Multiplicity is, negative 4 would be called a double root. If I were to look at the graph, there'd be a touch point at negative 4. It would bounce off the x-axis there. All right, hopefully we're feeling pretty good so far. It probably feels like you're flying just because we don't have to do all that testing that we did in the last lesson. All right, so our final example for the day, here we've got a quartic function, 4th degree, and again we're tasked with finding all the zeros of the polynomial. So let's see what the calculator can do. The fact that we're having more terms involved just means that we may be relying on the calculator for a little bit more. So let's see how this one works. Back to the y equals menu, clear out what we had. X to the 4th minus 5x to the 3rd plus 6x to the 2nd minus 10x minus 100. Just a quick check to make sure I didn't miss any powers or anything like that. I think we're good. Let's go to our table. Ooh, and right away I spot negative 2. Okay, so we'll use that x equals negative 2 to get things started. If you're following along with the note packet from my class, you may have a different polynomial. Please use this one instead. This is a 4th degree, so I'm expecting 4 zeros, either real or imaginary, to show up. And from our calc table, x equals -2 is a 0. So let's divide that one out, hopefully see our 0 remainder. We don't skip over any powers, no 0 placeholders necessary. We covered in the first part of chapter 4. Oh, hold on. Oh, no, we're good. All right, so kind of move through synthetic a little bit faster there. We should be pretty well practiced with that by now. So now I've got this new depressed polynomial. Go ahead and change colors here. X to the third minus 7x squared plus 20x minus 50. And as you can tell, we're left with a cubic function. However, I can't do factor by grouping, so I've ended up with a place where I'm not factorable yet. I need to try and find another 0. I need to keep working with that polynomial in black to try and divide it up a little bit more. All right, so let's see what we get there. Let's go back to our calculator. -2, or yeah, -2 works. Let's see if we can find another one. 5. Okay. So we'll do this work in blue. So our calculator also told us that x equals 5 is a 0. 5 goes into the box, and then I'm going to use this polynomial, that 1, -7, 20, -50. And I'm hoping that I can continue to divide that down to something that I can use quadratic formula or factoring or square roots. So we drop down the 1. Hey, we're good. 0. Things are shaping up pretty nicely right there. So at the end of this synthetic division, realize that our calculator gave us 2 out of the 4 zeros right here, just out of that table. We're left with x squared minus 2x plus 10. Where does that stuff equal 0? Those are going to be our remaining roots. I'm looking at magic numbers. I can't think of 2 numbers that would multiply to be 10 and add up to -2. So it's looking like this is not factorable. We better switch to quadratic formula. So find the solutions here. X equals opposite of b plus or minus the square root of b squared minus 4 times 1 times 10 all over 2 times a. Okay, I'm seeing why we weren't having anything else show up in the table, or why we couldn't have magic numbers. If we look under that square root, that radicand is going to be negative. We're dealing with imaginary stuff. Underneath the radical, we have stuff that makes -36. And that's an imaginary number. It's I times 6 all over 2. So x equals 2 over 2, 1, plus or minus 6i over 2, 3i. So to finally answer our question, the zeros we got for this polynomial were -2 and 5 out of the calculator. We had 1 plus 3i and 1 minus 3i, those conjugates, complex conjugates that showed up when we did our quadratic formula at the end. That's 1, 2, 3, 4 zeros for our 4th degree polynomial. All right, so I really hope that this lesson has shown you, it really is a nice learning experience to go through all the work that we did in the first part of 4B.3 and just kind of do that grinded out by hand mathematics, and then see how much the technology has allowed us to take a lot of the guesswork out of math. So I hope you've appreciated how those 2 lessons kind of come together to help us find all the zeros of a polynomial, and maybe we have a little bit more appreciation for our calculator now too. That thing does a heck of a lot, doesn't it? So thanks for watching, and good luck with your math work.